Woohoo! This one's going for ages.
Oh, that's superb.
Joel.
Oh. A magnet's made up of north and south poles, and it is the attraction. So in this, the south pole wants to attract the north pole, but the same poles repel each other, you see. So that spins round. Okay, so I'm drawing the magnetic field lines of this magnet, and I'm showing this with the compass. So the arrow's pointing in towards the south pole, so I'll just quickly draw that on. And it shows that it's pointing away at the north pole. So draw that on. And if we go around in a circle, it shows how it's pointing away and then goes in towards. So I'll draw that. Like that. And how there it's pointing inwards at a different angle. And there it points outwards at also a different angle. Now we would expect the other side to be just the same, like that. So let's just see if it is in the compass needle. So if you watch the needle, there it's pointing inwards, yeah. So we bring it round, so that's what it shows. And then there, yeah, that's exactly what I expected. So this is a liquid filled with iron filings. They're just metal. This is the magnet. And you put it there, then you'll see how the magnet's strongest there, so it's straight, but it's weaker around there and it curves round. And that's what's shown there. These are magnetic field lines.
So basically what we've got here is a spinning top, and as you can see it doesn't want to stand upwards like that. But if you spin it, it does stay upwards. This is something called angular momentum. So angular momentum basically is a spinning object remains standing up. Let's speed it up a bit. It's not fast enough. And you just put it in any position it wants and it'll stay there, apart from it will begin to precess around, as you can see. This is similar with the spinning top on the magnet. As it's north and north pole, if you let go, it will flip over and go north to south pole, as you can see. But if you give it angular momentum, it stays upright, the north and north pole, and so it won't fall over, like that. Okay, so basically we've got here is a copper tube and an aluminium weight, and as you would just expect, it falls out just due to gravity. Here we've got a similar cylinder, exactly the same size.
Okay.
So both going to just drop in, but this takes quite a lot longer. So why is it falling down slow? Well, with the aid of this contraption, which is just a very precise ammeter, we will see why. As it drops down, the magnet induces a current through the copper, and which repels the magnet back up the tube to slow down the effects of gravity, as you can see. The reason why the magnet slows down instead of speeding up is basically because there's a positive current, but if the current was negative and if the magnet did speed up, that would mean there would be free energy, because as the magnet speeds up, this would induce a higher current, which would then cause it to speed up further, which would induce a higher current, and effectively you'd have free energy. So as I said, we can put this in liquid nitrogen to see the effects. First.
Not forgetting the safety.
Copper cools down, it reduces the resistivity, or the resistance within the copper, so it should induce a higher current. So we'll see if that hypothesis is correct. also falls a lot slower, so it shows it is increasing have a higher current, so
Yep.
I would say we were correct.